Hello everyone, welcome back for part 2 of the 8.1 notes where we're talking about sequences and series still. In this case we're actually seeing our first example of a series. Before we just had sequences, which are just a list of numbers that go in order basically. Here a series is where you take a sequence and you add them up. So we have this little symbol over here. This one, it's a capital Greek sigma, and of course sigma, like sum, they both start with an S, and so it's the sum of a sequence. And so what it's talking about is basically, in this case, why don't we call this one 3k minus 8? We can call this like a sub k. And basically what we're doing with this summation is we're taking a sub 1, because we're counting here in this case, k is being used in this way. It's being used as an index, which index is kind of like a counting, the way that you're counting. And so the index, it's going from 1, and so this 1 over here, this would be considered the lower limit. It's going from the number 1 as the index, so a sub 1, up until the upper index, everything in between as well, up to the upper limit of 3, and then we would stop at 3. So it's going a sub 1 plus a sub 2 plus a sub 3. That's basically what it means. The sum from 1 to 3 of 3k minus 8. We're doing this one. So we're doing 3 times 1 minus 8. Oops. And then we're adding to it 3 times 2 minus 8. And then we're going to add to that one 3 times 3 minus 8. And then we will just come through and calculate these. So the first one, it goes 3 minus 5, or 3 minus 8 is negative 5. And then it goes 6 minus 8 is negative 2. So we're adding these up. And then it's going 3 times 3 is 9 minus 8 is going to be positive 2. And so we're adding 2 to that one. Negative 2 and positive 2, they just cancel, so it just becomes negative 5. And so that is how the series is going to work. We can try just another one here, where we will have some kind of funny thing here, which this one, negative 1 then raised to some powers, this is going to cause the signs to alternate. So I will say alternating signs. That's basically the only thing that this negative 1 to the j plus 1 power will contribute to this one. It will alternate the signs, and we just have to determine basically is it going to start with a positive 1 or is it going to start with a negative. And so here we're adding up, we're taking the sum from 3 to 5 of this thing. And so if we plug in 3 for the first one, it's going to go negative 1 times 3 plus 1, and then it's going to go 3 times 3 inside of there. So it's basically going to be, notice on the first one, 3 plus 1 is 4, so this is an even number. It starts with even, so when we go negative 1 to an even power, this will just become 1. So we're going to start out with a positive number, and then we're going to add negative 1 to, in this case, j will count up from 3. Now we're on 4, so we'll go 4 plus 1, and then times 3 times 4, and then we're going to add up. Now we're on to 5, which is the last one, and it's going to go plus 1, and then it's going to go 3 times 5. And so we're adding these numbers. Here, when we go to an even number, it will just go to the first power, so it would just go 9. When I say to the first power, I mean times 1, because of course it's an even exponent onto negative 1, so it would just become positive 1. Positive 1 times 9 is just 9. Then it will go negative here, so it will go minus 12. And then here it will go even power again, so it will go positive 1, so it will go plus 15. And then we're just adding these up. This will go 9 minus 12 is negative 3 plus 15, so basically we're just getting 12 for this one. That'll be the result for this one. Now, there is something that's possible to do with these sequences and these series, is that we can change the index. Basically, we can change it freely. We'll see an example here of changing the index for one of these sums. These sums are actually all supposed to be the exact same, but we will see that to go from this I to this j that it's talking about, you notice here the I is counting starting at 1, but the j is starting at 0. So we can actually make a substitution where I is always just 1 more than j. So we can say that I is j plus 1. And then if we want to plug in that for I over here, we can plug in for I over here, see what is the new starting, what is the new lower limit, what is the new upper limit, and then what is the new formula for the sequence. We plug in this I, and we would basically get that here, these are all I numbers. We could also, we just don't write I equals, but this 4 is also an I. So we can say that we're basically going from j plus 1 is 1 up until j plus 1 is 4 of the thing j plus 1 squared. And so here we can solve for what these j's are. Of course, if we subtract 1 on both sides, it will go 3 on top, it will go 0 on bottom, and we could just simplify that one and we could get this. And then you notice to go from here to here, we could do something as well. To go from the j's to the k's, here j is starting from 0, but k is starting from 2. So basically k is 2 more than j all the time. And so we can make this kind of a substitution. Here though we want to substitute for j, so we should subtract 2 on both sides. And we would get this other, it's an equivalent expression that goes that j is just 2 less than k. So j is k minus 2. We plug that in for all of these j's. So it'd go from k minus 2 equals 0 up until the point when k minus 2 is equal to 3. And then this one will go, instead of j plus 1, it will go k plus 1. So j is not plus 1. It will go our thing for j, which is k minus 2. I'm just substituting that for j. It's going k minus 2 and then plus 1 and then squared. We end up with something like this. We'd want to simplify everything around. Here we can add 2 to both sides, so it's going until 5. Here we add 2 to both sides, so it goes from k equals 2. And then in here, negative 2 plus 1 becomes negative 1. And you'll see that we end up with the same thing there. So we can do that where we can substitute in different values for these limits. The limits as well as the definition for each term of the sequences as well, using a different index. We don't change the sum at all. These sums will all be the same. We would get the same number by adding them all up, but we just achieve this thing of changing the index. And sometimes it can be convenient to do that. It can help us simplify a problem. But we're going to see here the last kind of an exercise that we're going to do for Chapter 8, which is where we are going to practice writing a sum using the summation notation. And it might help here to develop a little expression for what each one of these terms are, these a sub k terms. Notice I'm calling them a sub k now. Sometimes they were called f of n, or sometimes they can be called a sub n. These are all the same. It really doesn't matter. I have k on the brain from doing this problem previously that we just did with the series. And so these are all the same as long as we understand what we're using as an index. We could also use an I over here, or an L. We could do anything at all, as long as we're talking about the same thing. So here I'm going to come up with an expression for the general nth term, or in this case the kth term. So the kth term here, you notice always these numerators, what's happening to them. And this is going to be a little bit of, not really guess and check, but you'll have to see if you get some ideas here for how we're going to describe each one of these terms. You'll just have to check, make sure it works for all of the terms. You could get kind of an impression of what's going on here. Of course, every term goes over 5, so our general term should go divided by 5. And then what we have in the top, these ones 2, 4, 8, 16, 32, these are all powers of 2, so it's going 2 to some power. And it's actually, since the first one goes 2, that's 2 to the first power, so it just goes 2 to the kth power. And then it's going from whenever k is equal to 1, because that goes 2 to the first power, up until 32, which is 2 to the 5th power. So we're doing a sum here for whenever k goes from 1 up until 5 of the thing 2 to the k power over 5. And it looks like that's doing it for us. We have also, for example, number 15. You notice something funny is happening between here. It goes from negative to positive to negative to positive. So we have an alternating sign, which means our general expression, I will call them a sub n. The nth term, it's going from negative to positive all the time, so the first term needs to be negative, which means this should just go to the n power, because the first one should go negative 1 to the first power, which is negative 1. And then it's multiplying times something here. You notice the top is always doubling, it's always going times 2. The bottom is always tripling, it's going like times 3. So this would be what happens when you multiply 2/3 times itself. 2/3 times 2/3, it will multiply the top times 2 always, and the bottom times 3. And then it's just going also to the n power. So we could actually put these inside of the same power, going negative 2/3 to the n power, that's the general term. And then we're adding them up from whenever n is equal to 1 up until here goes 16 and 81. Those are where 2 and 3 are raised to the 4th power respectively. So it goes up until the 4th of this thing, negative 2/3 to the n power. And so that does it really for what we're doing with series. We're not even going to get into really the details about like arithmetic series, geometric series, or these kinds of sequences as well. There's so much left in this subject that would be wonderful to talk about, but it's just not within the scope of this class really right now. So I hope that you'll have a chance to work with some series and sequences a bit more in the future. Thank you guys for watching these videos. This does it for Chapter 8 and for the class. But anyways, I hope this video was a help to you, and I will catch you later.